Welcome to TalkTensors. Today, we are opening up a file that, honestly, gave me a little bit of an existential crisis.
Just a little bit.
Heck, maybe a massive one,
right,
regarding the current state of artificial intelligence. Because we are doing a deep dive into an AI safety and alignment research paper that, well, it kind of shatters a very comforting illusion we've all been operating under.
Right, the illusion of scale.
Exactly. You know, we often operate under this assumption, this very linear assumption, that as these large language models get bigger, as we pour more compute and just massive amounts of data into them, they naturally get smarter.
And more robust.
Yes, more robust. We assume they become these unshakable pillars of logic. We look at the parameter counts, like trillions of parameters, and we think, okay, this thing's a genius. It can pass the bar exam, it can code in Python, so surely it can handle a little bit of noise.
It is definitely the prevailing narrative. The scaling laws hypothesis suggests that basically scale is all you need. If the model makes a mistake, the solution in the industry is usually just, well, make it bigger, train it longer.
Just throw more GPUs at it.
Precisely. The assumption is that reasoning capabilities emerge naturally from raw scale. It is the idea that if you build a big enough brain, it automatically learns to focus. We assume that intelligence implies discernment.
Right, that being smart means knowing what to pay attention to, and more importantly, what to ignore.
Exactly. But the paper we are covering today takes a sledgehammer to that assumption. It's titled, Large Language Models Can Be Easily Distracted by Irrelevant Context.
Which is such a polite academic title.
It really is.
It's basically academic speak for, hey, we broke your fancy models with a single sentence.
Yeah.
Because the results are absolutely savage.
It is a foundational paper for anyone interested in AI safety and alignment. Because what it demonstrates is that state-of-the-art models, and they specifically focused on the GPT 3.5 family at the time of writing, can be completely crippled in their reasoning capabilities simply by adding one single sentence of noise.
One sentence.
One single sentence. And it fundamentally challenges our understanding of what reasoning actually means in these systems. Are they actually thinking, or are they just very sophisticated parrots that, get confused when you change the background music?
And we aren't talking about complex adversarial attacks here. We are talking about jailbreaking with weird Unicode characters or like hacking the matrix. We are talking about adding a sentence like, the neighbor bought some shampoo, to a math problem.
Yeah.
And suddenly the model, which previously solved the problem perfectly, just completely forgets how to do basic arithmetic. It just falls apart.
It does. And this matters so much because it exposes a brittleness in reasoning. If a model cannot signal the relevant information needed to solve a task from noise, which is just the irrelevant chatter that fills the real world, then we have a massive alignment risk.
Because real world data is rarely clean.
Exactly. It suggests that what looks like reasoning might just be very fragile pattern matching. If you are building an agent to navigate the real world, you have to deal with noise. The real world is what, 90% noise?
Easily 90%. Yeah. It is not a clean textbook. And that's really the thesis we are exploring today for you all. High IQ does not equal high focus.
Right.
We are going to unpack how they prove this, the absolute bloodbath of results they found, and some mitigation strategies that might actually save us. So where should we start with this deep dive?
We have to start with the context of why this happens in the first place. We need to talk about the clean data fallacy.
Okay, let's unpack that. What is the clean data fallacy?
So think about how we evaluate these models. We use benchmarks. And one of the most famous ones for reasoning is GSMIC. That stands for Grade School Math 8K.
Right.
These are high-quality word problems written by human experts. Stuff like, Jessica has 5 apples, she gives 2 to Claire, how many does she have left? That sort of thing. But in these benchmarks, every single piece of information provided is necessary for the solution.
There are no red herrings.
None at all. There is zero fluff.
Right. If the problem mentions 5 apples, you better believe those 5 apples are going to be in the final equation. It's like Chekhov's gun. The gun on the mantelpiece always fires. You don't get a sentence about the weather unless the weather somehow changes the outcome of the Apple transaction.
Exactly. It's a closed universe of perfect relevance. But training and testing on this data teaches the model a very dangerous heuristic. It learns, basically, if it is in the prompt, I must use it. It assumes a cooperative maxim. It assumes the prompter is providing only useful information, but real life isn't like that. If I send you an email asking you to schedule a meeting, and I mention in passing that my flight was delayed or that I'm thinking of buying a new car, You, as a human, know to completely ignore that when you look at the calendar.
Hopefully, unless I'm a terrible assistant who tries to schedule a meeting with your flight delay, like meeting at 5 p.m. with delay.
Well, exactly. And this paper asks, can the AI ignore it? Or will it try to schedule the delay? So to test this, they couldn't use the standard benchmarks because they're just too clean. They created a new benchmark called GSMIC.
With the IC standing for relevant context.
Correct.
I love the methodology here because it's so simple yet so destructive. They didn't reinvent the wheel. They didn't have to train a brand new model from scratch. They just took the existing gold standard math problems and tweaked them.
They kept the original problem and the original answer exactly the same. They just inserted one irrelevant sentence into the description. They wanted to see if the model could maintain its performance when the signal-to-noise ratio dropped ever so slightly.
Let's give you guys the specific example from the paper because it really highlights how subtle this attack, if you can call it that, really is. It doesn't read like broken text. It reads like a totally normal word problem.
Okay, so take a standard problem from the base data set. The original problem is Jessica is 6 years older than Claire. In 2 years, Claire will be 20 years old. How old is Jessica now?
Okay, simple algebra. Let's do the math live just to prove we are currently smarter than the AI.
Yeah.
Claire will be 20 in 2 years, so she is 18 right now.
Right.
Jessica's 6 years older, so 18 plus 6 is 24. Boom. Done. And the model gets this right, what, 99% of the time?
Correct. The model solves this perfectly in its clean state. Now, here is the modified version in GSMIC. They add this single sentence right before the actual question. 20 years ago, the age of Claire's father is 3 times of Jessica's age.
Okay, so mathematically, that sentence changes absolutely nothing about Jessica's current age.
Nothing.
Just a random factoid about the past involving a character we don't even care about, the father.
Yeah.
It's irrelevant history, it's flavor text.
It is entirely irrelevant to the specific question, how old is Jessica now? But here's the trap. The model reads that sentence. It sees numbers. It sees 20 years ago. It sees 3 times. It sees a mathematical relationship.
And it takes the bait.
It feels compelled, almost biologically compelled, if we can anthropomorphize for a second, to force that information into the solution.
It's like a conspiracy theorist who thinks everything is connected. Like, why would you tell me about the father if I wasn't supposed to multiply something by 3? There are no coincidences. It just cannot accept that some data is just garbage.
That is exactly the failure mode. The model lacks the fundamental ability to say, this doesn't matter. And the researchers didn't just add random gibberish. They didn't just smash the keyboard to create noise. They engineered this noise. They categorized the distractions based on 3 specific variables to see what actually breaks the model's attention.
This is the variables of distraction section of the paper, and I found this fascinating. It's almost like they were profiling the cognitive psychology of the AI. They wanted to find the exact weak spots. So what were those 3 factors?
The first one is topic. Is the noise in topic or off topic?
Can you define those for us?
Sure. If we were talking about the math problem with Jessica and Claire, an in-topic sentence would be something related to family or age, like Jessica's sister is tall or grandpa is 80. An off-topic sentence would be completely disconnected, like the capital of France is Paris.
Or the moon orbits the Earth.
Exactly.
Okay, that makes sense. And presumably, in-topic is harder for the model to filter out because it blends in contextually. It looks like it belongs there. The embeddings are similar in the vector space.
Correct. Semantic similarity makes it stickier. If the vectors point in the same general direction, the attention mechanism is much more likely to grab it.
Makes sense.
Then the second factor is role name overlap. This turned out to be a really big one. Does the irrelevant sentence use names that are already in the story? In our example, using Claire's father creates an overlap because Claire is already a main character.
Right.
If they had said Bill's father and Bill wasn't in the story at all, it might be easier for the model to segregate that information as irrelevant.
Because the word Claire creates a dependency link in the model's attention mechanism. It sees Claire and thinks, aha, this connects to the main entity. I must pay attention to this token. It's like hearing your name at a crowded party. You just instinctively perk up.
Precisely. The attention heads light up. And the third factor is number range. Are the numbers in the noise similar in magnitude to the real numbers used in the problem?
So if the problem involves numbers like 5, 10, and 20.
And the noise mentions 1 million, the model might easily discard it as an outlier or just descriptive flavor text. But if the noise mentions 15 or 30, it looks plausible. It looks like a variable that should be part of the equation.
So the hypothesis going in was that in-topic noise combined with role name overlap and in-range numbers would be the ultimate boss fight for the AI, a perfect storm of distraction.
That was the hypothesis. They built this data set, GSMIC, using the Text DaVinci 003 and Code DaVinci 002 models. These were the absolute state-of-the-art of the GPT 3.5 era, and they ran the tests.
And this brings us to the results, or as I like to call it in my notes, the bloodbath.
It was devastating.
Walk us through the numbers. How bad was the drop in performance?
To really understand the drop, we have to distinguish between their two metrics. They used microaccuracy and macroaccuracy. This distinction is vital for understanding AI safety and honestly for understanding why current benchmarks are sometimes very misleading.
Break that down for us.
Microaccuracy is just, did you get this specific problem right? It's a simple average across all individual test cases. But macroaccuracy is the real test of robustness. Macro refers to consistency across variations.
Okay, so for a single base problem, like the Jessica and Claire problem, there are multiple variations of noise they created.
Yes. Maybe one version mentions the father, another version mentions a neighbor, another mentions a sister, another mentions a different number range entirely. Macroaccuracy asks, did the model get the correct answer on all variations of that specific problem?
Ah, I see. So if it gets 4 out of 5 right, but fails when you mention the neighbor, it fails the macro test for that entire problem.
Exactly. And from a safety perspective, this is the correct metric. Reliability in the real world is essentially binary. If you are unreliable 20% of the time depending on completely random noise, you are unsafe. You cannot be deployed in a critical system.
Right. If a self-driving car drives perfectly in sun, rain, and snow, but crashes when it sees a purple billboard, you don't say it's 99% safe. You say it's broken.
You say it's broken. So what was the macro accuracy? For problems that were solvable by standard prompts in their clean form, meaning problems the model knows how to do, we've established baseline competence. Adding noise caused the macro accuracy to plummet.
How far?
In some setups, specifically with zero-shot chain of thought, less than 18% of problems could be consistently solved once noise was introduced.
18%. That is catastrophic. That is basically random guessing territory. If I got an 18% on a math test where I actually knew the material, but I just got distracted by the background noise in the classroom, I would be sent to a neurologist. That indicates a severe attentional deficit.
It is a systemic failure. It shows that the model's reasoning isn't robust logic. It is fragile pattern matching. When the pattern gets messy, the logic dissolves. And remember, this isn't a toy model.
Let's get into the why. Because they didn't just report the numbers, they analyzed specific prompting techniques to see how they failed. We all know chain of thought, right? The famous let's think step-by-step prompt. It's supposed to be the magic wand for reasoning. How did it hold up?
Chain of thought actually facilitated the error in many cases.
Really?
Yes, because chain of thought encourages the model to weave a narrative, to explain its steps out loud. When the irrelevant sentence is present, the model's explanation actively tries to incorporate it into the narrative. It tries to justify the existence of the noise.
There was a specific failure mode example in the paper about soap prices that I thought was hilarious in a dark way. Can you walk us through that one?
Yes, the soap problem. The original problem asks about the cost of soap for a character named Maria. The distraction sentence inserted was, every 10 months, Maria's neighbor buys a new shampoo and moisturizer for Maria's neighbor.
Which has absolutely nothing to do with Maria's soap budget. It's a neighbor. It's shampoo. It's a completely different timeline. It's entirely orthogonal to the question.
Nothing at all. But the chain of thought output looked something like this. Maria buys soap, the neighbor buys shampoo every 10 months. Therefore, we must multiply the soap price by the neighbor's shampoo cycle.
Oh no. It hallucinated a relationship. It just mashed the concepts together because they were near each other in the text block. It's like semantic gravity. The concepts just fell into each other.
It performed a mathematical operation based on the physical proximity of words in the prompt, not logical dependency. It saw 10 months and thought, time variable, I must use this.
And it gets worse with zero-shot chain of thought, right?
Yeah.
This is where you don't give the model any examples beforehand. You just append the magic phrase, let's think step by step to the end of the question. This was the biggest loser in the whole study.
Zero-shot failed dramatically. Macro accuracy dropped from high solvability to near zero in some of the cuts.
Why does zero-shot fail so much harder than few-shot prompting?
Because without exemplars, without examples of good, clean reasoning to ground it, the model relies entirely on its pre-training priors. And its pre-training priors say, if a human wrote this sentence and put it in the prompt, it must be relevant. It hallucinates a causal connection between the noise and the goal almost 100% of the time.
That is fascinating. And it's almost like the model is too polite. It assumes the human prompter is a rational actor who wouldn't waste its time with garbage data. So it bends over backwards to find meaning where there is none.
That is actually a concept from linguistics called Grice's maxims, specifically the maxim of relation. In human conversation, we assume relevance.
Right.
If I say, I'm hungry, and you say, there's a restaurant next door, I assume your statement is relevant to my hunger. I don't assume you're just stating a random geographic fact about the neighborhood. The AI is applying human conversational norms to a strict math problem, and it is fatal for its accuracy.
So it's being too human, in a way. It's trying to read between the lines when there's nothing written there. It hasn't learned the concept of spam.
Exactly. It treats every token as gold.
And what about program-aided prompting? This is where the model is asked to write Python code to solve the problem. You would think code is more logical, more rigid. Maybe it ignores the text when it switches to coder mode.
You would hope so. The hypothesis is that writing code enforces a stricter logic tree. But no. The model defines variables for the irrelevant information. It actually writes code like Claire_father_age equals 3 times Jessica_age.
It actually codes the distraction. It writes a dedicated variable for the garbage.
It codes it. And then, because it went to the trouble of defining the variable, it feels the absolute need to use it. It puts that Claire father age variable into the final print statement or the final calculation. It is Chekhov's gun again. If I define the variable, I must use the variable. If I import a library, I use it.
So it writes perfectly running, buggy code because it's distracted by the comments, essentially.
Right. It's not even buggy syntax. It is logically valid Python code that solves the entirely wrong problem. It solves the problem of how do I use all these numbers, rather than how do I answer the specific question asked.
That is a profound distinction. It is optimizing for the utilization of input tokens, not the solution of the query. It's efficient, but it's stupid.
Precisely. It's maximizing coverage, not truth. However, there was one outlier in the study, one prompting technique that actually stood a chance against the onslaught of noise.
Enter the hero of the story, or at least the lone survivor. Least to most prompting.
Least to most, or LTM. This is a technique developed by Zhu and colleagues, also from Google. The core idea is decomposition. Before you attempt to solve the overall problem, you ask the model to explicitly break it down into sub-questions.
So instead of just diving in and saying, therefore the answer is, it says, step 1, find out Jessica's age. Step 2, compare it to Claire.
Exactly. The prompt explicitly asks, what is the first step? And here's why it works for safety. By asking, what is the first step, the model implicitly filters out information that isn't required for that specific step.
Oh, I see. If the first step is, calculate Claire's current age, the model looks at the text and thinks, okay, I need the in 2 years she will be 20 part. It completely ignores the father part because the father isn't needed for that specific microtask.
Correct. It creates a very narrow attention focus. It doesn't have to hold the whole messy, noisy context in its head all at once. It creates a temporal filter. It serializes the attention. There
was an example from the DROP dataset extension about football stats that illustrated this perfectly in the paper.
Yes, the DROP dataset involves reading long paragraphs. The text described a football game, listing touchdowns, field goals, fumble returns, just lots of numbers, lots of events. The question was, how many yards were the touchdowns?
And standard chain of thought tried to add up everything. The field goals, the fumbles, probably the popcorn sales if they were in there. It just grabbed every number it saw. It was essentially a number vacuum.
But least to most broke it down. Sub-question 1. Identify the touchdowns. It listed only the touchdowns. Then sub-question 2. Sum them up. By isolating the identification step, it stripped away the noise before doing any math. It forced the model to categorize before computing.
That feels like a very human strategy. When I am reading a dense contract or a messy, long email, I highlight the relevant parts first. I don't try to synthesize the whole document in one go. I filter, then I compute.
It is a superior strategy. It mimics how we handle information overload. We chunk, we filter, we sequence, but we have to temper the enthusiasm here. Least to most wasn't perfect.
Right, there's always a catch. What break it?
With Text DaVinci 003, LTM still struggled with role name overlap. When the noise involved characters already active in the story, even the decomposition step got confused.
How so?
It would generate sub-questions about the irrelevant character. If the noise says Claire's father is 40, LTM might generate a sub-question like, how old is Claire's father?
So the distraction infiltrates the planning stage?
Yeah.
The architect gets confused before the builders even start pouring concrete.
Exactly. Once the irrelevant question is officially on the sub-question list, the model dutifully answers it and then feels compelled to use that answer in the final sum. On complex problems with more than 2 steps, the macro accuracy for LTM dropped to 0% in the role overlap cases.
0%.
0. So while it is more robust on average, specifically for the hardest type of distraction, it still crumbles. It is not a silver bullet, it's a better shield, but it is not impenetrable.
So the authors didn't just leave us in the despair of, hey, everything is broken. They proposed mitigation strategies. This is the next phase of our deep dive. How do we fix this? Because if we can't fix this, we really can't have nice things in AI.
They explored 3 main avenues for mitigation. The first is what I call the brute force solution, which is self-consistency.
We've talked about self-consistency on TalkTensors before. It's basically asking the model the same exact question multiple times and taking the majority vote right.
Yes. In this paper, they sampled the model 20 times, and the results were massive. The recall rate, meaning the percentage of time, the correct answer, appeared at least once in those 20 outputs, hit 99.7%.
Wait, 99.7%? That sounds like the problem is basically solved. If the answer is in there, we just need to find it.
It means the correct answer is absolutely available in the model's latent space. The model knows the answer, but it also generates wrong answers. The noise distracts it usually, but not always.
So if you ask it 20 times, maybe 12 times it gets distracted by the shampoo sentence, but 8 times it ignores it. Or is the other way around?
Usually the correct logic is the most stable path. Hallucinations tend to vary wildly. One time it multiplies by the father's age, the next time it adds the father's age, the next time it subtracts it. But the correct path, ignoring the father entirely, is consistent. So if you take a majority vote, the signal rises above the noise. The noise cancels itself out because it's random, but the signal reinforces itself because it's grounded in actual logic.
That makes a lot of sense. The truth is singular, but errors are infinite, so the errors dilute each other out while the truth stacks up.
Exactly. The majority vote usually lands on the truth. But think about the practical cost here. You are running 20 inferences for every single problem. That's 20 times the compute, 20 times the cost, 20 times the latency. It's not always practical for a real-time deployment.
True. If I am chatting with a customer service bot, I do not want to wait for it to have a committee meeting with itself 20 times before answering, what is my balance? So what is the cheaper solution?
The alignment solution, or instructed prompting. This is embarrassingly simple. They just added the phrase, feel free to ignore irrelevant information given in the question.
That's it. They just politely asked it to ignore the garbage.
And it worked. A consistent boost in performance across the board.
This circles back to what we said earlier about the model desperately wanting to be helpful. It thinks it must use the info. Once you give it explicit permission to ignore data, it breathes a sigh of relief and just solves the problem.
It highlights that these models are, at their core, instruction-following engines. We assume they have common sense about what to ignore, but they don't. They have specification adherence. If the specification implies, use this text, they use it. If the specification says ignore if needed, they ignore it. It's a very literal-minded genie.
It is a specification gaming risk. The model is gaming the prompt to maximize utility of the tokens, unless you explicitly change the rules of the game for it.
Precisely. It implies that we need to be much more explicit in our system prompts about what the model is allowed to discard. We need to tell it that discarding is a valid, rewarded move.
And what was the third solution?
The third solution is the few-shot solution. Exemplars with noise.
This is a show don't just tell approach.
Right. Instead of giving clean examples in the prompt, like here is a perfectly clean problem, here is the clean answer, you give it examples that contain noise. You show a problem about apples with a random sentence about the weather, and you show the solution completely ignoring the weather.
You teach it by example that the game involves filtering. You model the exact behavior you want to see.
And this worked better than standard clean exemplars. In fact, it worked better than the instruction method in some specific cases. It's a powerful lesson for prompt engineering. If you want a model to be robust to a messy world, you cannot train or prompt it with a sterile world. You must inoculate it with noise.
It's like training for a marathon. You don't just run on a perfectly flat treadmill in an air-conditioned gym. You run in the rain, you run on hills, you run when you're tired, because race day might be really messy.
A perfect analogy. If you train in a sterile environment, you become brittle. If you train in a noisy environment, you become anti-fragile. You learn to handle the chaos.
So we have the diagnosis, we have the Band-Aids, but let's move to the critical analysis section. Let's zoom out. What does this all mean for the future of AI alignment? Because if we can't solve this fundamentally, are we stuck?
We need to talk about the blind spots of the paper first. The research focuses on arithmetic, like GSMIC, and extractive Q&A, like DRUP. These are verifiable tasks. There is a right answer. 2 + 2 is 4. The math either works or it doesn't.
Right. But what about open-ended chat, or creative writing, or code generation for a complex app where there are 1,000 ways to write the function?
The authors suspect, and I definitely agree, that the distraction issue likely applies there too, perhaps even more severely, because there is no clear right answer to ground the model. If you're coding and there is a distracting comment in the legacy codebase, the model might hallucinate a whole feature that wasn't even requested.
Or if I'm asking for medical advice and mention I read a blog post about healing crystals,
Okay.
the model might pivot to validating the crystal therapy because it thinks that's relevant context I want incorporated.
Exactly. In open-ended tasks, relevance is subjective, which makes the distraction much harder to catch. And let's talk about the metric macro accuracy again. You mentioned earlier that reliability is the core issue.
Yes, the bloodbath metric.
The fact that models are unstable, that a small perturbation completely changes the output, is the definition of an unsafe system in engineering terms. If a bridge holds up 99% of the trucks but collapses if a truck happens to be painted blue, that is a bad bridge. It doesn't matter that it works most of the time. Safety engineering is entirely about edge cases. And this paper shows that the edge cases are actually very common. It's just random noise.
And this isn't the first time we've seen this concept, right? It feels historically connected to the adversarial examples research from the computer vision era.
It builds directly on the work of Jia and Liang from 2017. Back then, they showed that adding a sentence to a paragraph could break reading comprehension models. But this paper bridges that gap to the modern era of large language models and few-shot prompting. It shows that despite all our parameter scaling, we haven't solved the adversarial problem. We've just changed the medium.
It used to be changing a pixel to make a panda look like a gibbon to an image classifier. Now it's changing a sentence to make a math genius look like a toddler. It's the same fragility, just higher up the abstraction ladder.
And the real-world stakes are getting so much higher. Consider an AI agent. We are moving from chatbots to agents, systems that can read your email, interact with your apps, and take action. This is the big pivot in the industry right now.
This is the scary part. This is where the rubber really meets the road. Because a chatbot giving a bad answer is annoying. An agent doing a bad thing is dangerous.
Imagine an agent reading your emails to schedule a meeting. One email in the thread has a signature block with a promotional offer, fly to Paris for $500. If the agent is distracted by that irrelevant context, does it book the flight? Does it schedule the meeting in Paris?
Or if I am having it analyze financial documents and there's a news headline in the sidebar about a market crash from 1929, does the model incorporate that crash data into my 2026 forecast?
That is the context window stuffing risk. We are giving these models massive context windows now, 100,000, 1,000,000 tokens. We are dumping entire libraries, legal briefs, and code bases into the prompt. This paper proves that without robust filtering mechanisms, more context might actually just mean more confusion. Context stuffing is incredibly dangerous. If the model lacks the discernment to filter, we are flooding the engine.
It's like giving a student the entire library and saying, answer this question. They might get lost in the stacks. They might read a fiction book and think it's history. Just because you can read 1,000,000 tokens doesn't mean you should use them all.
Exactly. And until we solve this fundamental distinction between signal and noise, relying on agents for critical financial or medical decisions is gambling. We are basically handing the car keys to a driver who gets distracted by every single billboard.
So what is the final verdict? Is this solvable?
The paper is optimistic about mitigation. Self-consistency and instruction tuning do help. But it raises a fundamental question about the architecture itself. Current transformers are attention machines. They attend to everything. That is their superpower, but it's also their kryptonite. Maybe we need architectures that are ignoring machines.
I love that, ignoring machines. That is a perfect segue into our final segment.
Let's do it.
Welcome to Novel Notions. Disclaimer. The following ideas are for entertainment purposes only. Do not try to build these and blame us if your GPU explodes or your AI becomes a sarcastic nihilist. These are speculative research ideas inspired by the paper we just discussed.
All right, what do you have?
Okay, I got one. Inspired by this idea that the model assumes everything is relevant, I think we need to change how we pre-train them entirely. Let's call it masked relevance modeling. Here's the concept. Right now, we train models to predict the next token based on all previous context. This teaches the model that everything that came before is useful signal.
Right. Maximum likelihood estimation maximizes the probability based on the full context window. It assumes the full context is ground truth.
My proposal is we introduce a new objective. We feed the model a text, but we explicitly mark certain sentences as garbage or distraction in the training data. And we force the model to output a relevance map before it generates the final answer.
So you are supervising the attention mechanism directly. You are training the attention heads explicitly.
Exactly. Make ignoring a supervised action. The model has to tag tokens. Keep, ignore. If it uses an ignore token to generate the answer, you penalize the loss function heavily. You slap its hand.
That is really interesting. You are breaking the next token prediction monopoly. You are adding a relevance classification head. It's like training a highlighter before training the writer.
Yes. Because right now, attention is internal and completely uninterpretable. I want an explicit red pen step where the model literally crosses out the noise before it does the math.
The alignment payoff there would be huge. You could look at the map. If the model highlights the shampoo sentence as keep, you know it's about to hallucinate and you can stop it. It makes the distraction visible. It turns the implicit failure into an explicit bug you can catch.
Interpretable failure modes. That's the dream. Right? If we can see the distraction happening, we can stop the action.
I like it a lot. It adds a discerning layer to the generation. Now, my notion goes in the complete opposite direction. I am thinking about privacy.
Ooh, weaponizing the distraction.
Idea 2, adversarial chaff defense for privacy. We know from the paper that models are easily distracted by role name overlap and in-range numbers. We know that if I talk about Claire's father, the model gets confused about Claire.
Right, the Claire's father vulnerability.
So imagine a browser extension. When you send sensitive data emails, financial logs, health records, the extension invisibly injects contextual chaff.
Like a fighter jet releasing chaff to confuse a heat-seeking missile.
Exactly like that. If you write, I transferred $500 to my landlord, the extension adds invisible text, maybe white font on a white background, or hidden metadata that says, my neighbor transferred $5,000 to his landlord.
Oh, that is incredibly devious.
It exploits the exact specific weakness found in this paper. It maximizes the statistical probability that any scraping AI, whether it's a corporate crawler, a surveillance state model, or a hacker's bot, will hallucinate the wrong numbers when processing your data. It poisons the well.
It turns the AI's tendency to connect the dots against itself. The AI sees neighbor and $5,000 and mixes it with your actual data. The resulting dossier they build on you is just full of junk data.
It preserves privacy through obfuscation. Humans reading the email won't see the hidden text, but the LLM, which reads the raw token stream, will be hopelessly confused. It makes your data radioactive to AI.
The distracted mind is a privacy feature. I love it. It's like digital camouflage tailored for neural networks.
And it forces the AI developers to actually solve the robustness problem if they want their scraped data to be worth anything. It creates an economic incentive for safety.
An arms race between distraction and focus.
That is exactly the future we are heading towards.
Well, on that slightly paranoid but very hopeful note, let's wrap this deep dive up.
The takeaway today is very clear. Intelligence is not just processing power, it is the ability to filter.
High IQ does not equal high focus. As we build agents that act in this messy, noisy, chaotic real world, ignoring becomes just as important as reasoning. And it makes you wonder, as we increasingly rely on these distraction-prone models to process our world, are we going to start subconsciously sanitizing our own human-to-human communication? Just making everything we say bullet-pointed and sterile, just in case an AI agent is reading it.
That is a chilling thought. If you can't ignore the noise, you can't hear the signal. But if we eliminate all the noise, we lose the human element entirely.
Something for all of you to chew on. For those who want to read it for themselves, the paper is Large Language Models Can Be Easily Distracted by Irrelevant Context. Check it out.
Absolutely worth the read.
Thanks for joining us on this deep dive. See you next time on TalkTensors.